and the first talk will be given by Olivier Hainaut in remote connected. Olivier, can you hear us?
Loud and clear. Can you hear me?
Olivier, can you hear us?
Yes.
Perfect.
Loud and clear.
So then please go ahead. You can start your presentation.
Okay. So let me share the screen and let's get started. Sharing. Okay. Well, hopefully you should see my screen soon, I hope. Yes. Okay. Well, since the beginning of the constellation saga, we have tried to quantify the impact of the satellites on observations. So for this talk, I will focus on spectroscopic observation. And the reason is that spectroscopy represents about 50%, over 50% of the data that we take with
recording in progress.
VLT. And many astrophysical parameters are derived from spectroscopy. So in imaging, when a satellite crosses the field of view, it leaves a trail, which is very easy to identify, even down to very low signal to noise. In spectroscopy, however, you extract a small fraction of the field of view with a slit, and then disperse the light with the spectrograph to get the record as a record of the flux as the function of wavelength. That's the spectrum. That's where you measure the various parameters. So in spectroscopy, we have either 1D or, in the case of a fiber spectrograph, no spatial information at all. So that means you won't see a trail. So a satellite crossing the slit will appear as an additional spectrum. If it's bright and isolated, it can be fairly easy to spot. But if it's faint and lost in another object, it can become really difficult. So how often does that happen? It depends, of course, of the number of satellites. We've discussed that before. We used to have 2,000. Now it's more like 5,000. Soon we could have 40,000 or even more. So for the simulation, we used 400,000 satellites. And we used the analytic simulation method that we described in our paper last year. David Galadi will talk more about it tomorrow. We also used a representative spectrograph, sorry, with a slit of 10 arc second and an exposure time of 1,000 seconds. And with the analytic simulation, we get a map of the sky, like here on the right, where the color code gives you the number of satellite trail per exposures for any place, any pointing of the telescope. Doing that for a series of elevation of the sun below the horizon, you get the evolution during the night. And so here you see the shadow of the Earth that covers more and more of the satellites. And in summary, you have the plot at the bottom right. And it shows that at the end of astronomical twilight, when the sun is at minus 18 degrees, we have about 10% of the spectra that are affected by a satellite. And if you take the average over the whole night, that gives an average of about 2%. That means one spectrum out of 50. So that's about one spectrum per night. That's the full 10 arcsecond slit. So point sources are less affected than that, but 2% is a good rule of thumb. Of course, the effect of a satellite trail on the spectrum will depend on the magnitude of the satellite. And we have heard many talks about photometric measurements. So this is a fairly old plot already, but it shows the range of magnitude of the satellite going from 5 to 10 or even a little bit fainter. But because of the very fast apparent motion of the satellite, they move about 1 degree per second, the satellite will stay very briefly in the slit of the spectrograph. And it's about 1 millisecond over an exposure that is of the order of 1,000 seconds. So that means that the satellite will appear 1 million times fainter than if it had stayed in the slit. So it's useful to introduce the effective magnitude that takes into account the ratio of these times. And for a typical satellite of magnitude 7, the effective magnitude will drop to magnitude 20 to 24. So that means that the spectrum of the satellite will appear as bright as if it had been of magnitude 20 to 24. Let's now compare this effective magnitude to the limiting magnitude of the spectrograph. So how faint an object can be observed with the spectrograph is obviously a function of the size of the telescope. Bigger telescope will see fainter objects, but it also depends on the resolution of the spectrograph. If the light is dispersed more, the spectrograph will be sensitive only to brighter objects. So here I plot again the effective magnitude of a satellite of magnitude 6, and here are the limiting magnitude of various spectrographs. In red, high resolution, you see that the limiting magnitude is much brighter than the satellite. So that means that these high resolution spectrographs are essentially completely blind to satellites. On the other side, you have low resolution spectrographs on large telescopes, and they can detect objects that are much fainter than the satellite. So here, these will easily detect the satellites, and the contamination will be easy to spot. The problem is the spectrographs here in the middle. So either high resolution well, this one is actually moderate resolution on a 4 meter, or low resolution on a 4 meter, medium resolution on an 8 meter. These are close to the limit. So the spectrograph can detect the satellite, but it won't be easy to spot it. So to investigate the effect of these hard to detect contamination, we used real data from the X-shooter spectrograph. And here in black, you have the spectrum of a hot star with X-shooter. And we added a satellite contamination by scaling the spectrum of a star that looks like the sun, scaled it to magnitude 6, and then accounted for the motion of the satellite. And the original spectrum in black, once contaminated by a satellite of magnitude 6, gives you the purple line, which is almost undistinguishable from the original one. If we decrease the exposure time, the contamination relative to the object is going to increase. And so you see the other lines are what happens if the exposure time decreases down to 20 seconds. So we've done a series of measurement of astrophysical parameters on hot stars, quasar, planetary nebula. All the nitty-gritty details are in our paper that's coming soon, I hope, really soon. And in short, for the original spectra, the abundances measured through the equivalent width will decrease by about 1%, down to 10% at very low signal to noise. The line profile is also affected. Electron density, for example, in planetary nebula is also affected at the percent level. So that means, first, that precision astrophysical measurements are going to be affected. And second, they are going to be super hard to detect. A change of 1% is almost hopeless to detect. So some caveats. What I've just said is for constellation satellites, but we will also have bright satellites. Hubble space station, blue walkers. There are very few, but they are very bright. So that means that even a spectrograph that normally would not be affected could be affected by these bright satellites. Also, we have to take into account the satellites that are on much higher altitude because their motion is much slower, and therefore the effective magnitude will be much brighter. And this is how a debris from a rocket was identified as a gamma ray burst at redshift 11, unfortunately. We have also other sources of contamination, asteroids. Many millions of them exist, but most of them are unknown. They do not, we have never observed them. And even though they are faint, any magnitude basically, their motion is so slow that the effective magnitude puts them in the range of these spectrographs. Other sources of contamination, meteors, airplane, cosmic rays, even been pipe smokers have contaminated spectra. So all these will cause faint or blind contaminations. So that means that no matter which spectrograph you use, beware of unconfirmed transient or weird objects or blind contaminations. So what can we do against these? Well, first, before the observations, we can hope and negotiate and beg with the satellite operators to have fewer satellites and keep them as faint as possible. We can also plan smartly the observations, either statistically using the analytical maps that we can produce. If you point in a good region of the sky, you can get a factor 10 or 20 or 50 less contamination than in a region where they are illuminated. We also had the talk from Harrison Krantz this morning that shows the depending where you point, the satellites can be much fainter. Thanks, Harrison. I stole this from you this morning.
Olivier, around 2 minutes.
Yeah, I'm virtually done. We can also compute the position of each satellite individually, but to be useful for spectroscopy, this must be done with a precision of about an arc second or better. And of course, the catalog, you will get only the satellites that are in the catalog. That's what PassPredict is planning to do. During the observation, we can have a camera that monitors the field of view, and we heard already from Genoveva this morning, and we will hear more next talk. That's what Foremost plans to do. But I would say the simplest is to split observations. If you take, instead of 1 hour exposure, you take 3 times 20 minutes, each of them will be much shorter exposure, and therefore it will be much easier to detect the individual contamination, and you will have reference comparison spectra. So it will be, you have a chance to detect a blind contamination. After the observation, be careful. If your spectrum looks weird, there might be a satellite or a contamination. We will also hear later that for surveys, machine learning can come to help. So, in summary, with 400,000 satellites, you can expect that on average 2% of the spectra will have a tail. This 2% scales with the number of satellites, the exposure time, and the length of the slit. Not all spectrographs are equal. High resolution ones are essentially blind to constellation satellites, but mid resolution and low resolutions are going to be affected. And with the risk that you can get very faint contamination that will give a small but non-negligible effect on the astrophysical parameters. So in terms of mitigations, keep the satellite faint, plan smartly. I would argue split observations is not the panacea, but it will help in many cases. And then we will have advanced mitigation methods like individual satellite forecasts, machine learning data processing, and for some telescope monitoring camera. So, thank you.
Thanks a lot, Olivier, also for the introduction of the next talk, which I'm going to use.